Hi everyone, my name is Alvi Monchel and today we will be discussing the activities in AG 104 Organic Chemistry, Course Pack 2, Chapter 2, and this includes the activity number 3 and 4. So let's dive right in. So to begin with, we see here on the activity 3, problem 2.1, we are going to identify the function groups of the following molecule. So we have here A, we will going to identify the function groups in the acrylic acid. So what you see there, I was able to answer two functional groups, the carboxylic acid and the alkene double bond. So how did I come up with that? So it's very simple. We see here in the substituent that is the carbon is double bonded with oxygen and OH. So that is carboxylic acid. And we also have here the double bond alkane. And now, many would have a challenge here or a confusion why this is not alcohol since we have here OH. So for me to illustrate that, so let's see here the OH, and if I put here the oxygen, now this would be an alcohol here since it is moved away from the carbon double bonded with the oxygen, and this would become a ketone. So we will see here an alcohol and a ketone instead. So but if we put the double bonded carbon to the oxygen closer to the OH, then that would be carboxylic acid. Now again, this is the double bond carbon is the alkene double bond. So number 2, we have here the aspirin. We have 3 substituent here, the hexagon hexagon shape, that is the ester, and again the carboxylic acid, which is the double bond of oxygen to the carbon and OH. So also we have here the arin, which is here you can see that the substituent, the oxygen bonded with the carbon and the carbon double bonded with the oxygen and also bonded with the CH3. Now we also have the letter C. We have here the glucose, and in here into glucose we can see here 6 functional group. The first one is the aldehyde, which is the carbon double bonded with oxygen and hydrogen. So the rest is an alcohol, which is an OH. See here this one first, 1, 2, 3, 4, and 5. So in total there is 5 alcohol and 1 aldehyde. Now here on the problem 2.4, you can see that clearly there. Okay, so we are going to draw structures for 5 isomers of C6H14. So 6 carbon and 14 hydrogen. So we can draw that as many types as you want. You can see here, and the most important thing we need to remember is that there should be 6 carbon and 14 hydrogen. So the first image you see here is the 1, 2, 3, 4, 5, 6 carbon and 14 hydrogen. We also have that here, this one, the same, and we also have this one. You can go about doing that. So actually, as long as in drawing the structure of the 5 of the C6H14, you can even do this one. So we have 6 carbon, 1, 2, 3. So a hexagon would be fine. So that's it. That would be a C6. So that is understandable. That would be C H2, CH2, 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 CH2. So what you can see there is the complete line chain of carbon, which is the 6, and the hydrogen we will count 2, 4, 6, 8, 10, 12. So since there would be a lack of 2 hydrogen, so we're going to erase just this one. We can add CH3 there, and also this one. You can also add CH3 here. So anything goes that way. So we will proceed to the problem 2.8. Here we are going to identify the carbon atoms in the following molecules as a primary, secondary, or quaternary. So this is actually very simple. We see here it is bonded in the first carbon chain. We have the primary, letter B, the secondary, letter C, the tertiary, and also a quaternary. Here in the problem 2.9, give the IUPAC names of the following alkanes. We have here the letter A, the 3 isomers of C5H12. That is C5, that would be petane. The 3 isomers of that would be normal petane, the isopatane, and the neopatane, which is, the IUPAC name is petane. We have here the letter B. We were going to count the what carbon chain that is closest to the end that has a branch with the longest one. So we see here the ethyl, CH2CH3. So we're going to begin our count here. 1, 2, 3, 4, 5. That would be petane for 5 as well. So here on the second carbon chain, the ethyl, that would be 2 ethyl. And on the third carbon chain, we have the methyl, and we can read that as 2 ethyl, 3 methyl petane for 5 carbon chain. And we have here letter C. Again, we're going to see what substituent closest to the end. So we have here, they have the same length or the same value. So we can count here, or here. So that would be 1, 2, 3, 4, 5. Again, that would be petane for 5. Since there is 2 methyl, we can add di for 2. So we can see here on the second carbon chain, the first, and on the fourth one, the second methyl. So we can write that down as 2 and 4 dimethyl for 2, petane for 5 carbon chain. And we have here the this compound, or this alkane. So we have here, we located that this is the longest chain substituent that is closest to the end. So we're going to begin our count here. 1, 2, 3, 4, 5, 6. So that would be hexane for 6. And on the second chain, we have the ethyl. That would be 2 carbon and 5 hydrogen. So 2 ethyl. We have here double substituent here on the 5th carbon chain. So 5 and 5. Di for 2 methyl hexane for 6 carbon chain. And on the problem 2.10, we're going to draw the structure corresponding to the following IUPAC names. So we can see here the 3 and 4 dimethyl nonane. So nonane, that would be 9 carbon chain, and we're going to put the substituent methyl, which is 2, on the 3rd and 4th carbon chain. So you can see that here 1, 2, 3, 4, 5, 6, 7, 8, 9. And on the 3rd and 4th carbon chain, we're going to add the methyl, 2 methyl. You have here the letter B. Again, 3 ethyl, that would be on the 3rd carbon chain, the ethyl, and 2 dimethyl on the 4th. So you can add so we can see here the heptane. So that would be 7. 1, 2, 3, 4, 5, 6, 7 carbon chain. We're going to place the ethyl on the third carbon chain, since 3 ethyl, and 2 methyl for di on the fourth carbon chain. We have this one, and we have here also the letter C, 2 dimethyl, 2x2 dimethyl for propylocane. So since it would be dimethyl, which is 2 on the second carbon, there would be 2 chain, so that's CH3, and the propyl, which is CH2, CH2, and CH3, which is bonded on the fourth carbon. So we will number the carbon chain. Since it's octane, that would be 8. 1, 2, 3, 4, 5, 6, 7, 8, 4 octane. And the last one, we have here the letter D, the 2, 2, and 4 trimethyl heptane. So again, methyl stands for CH3. So since this is heptane, that will be 5 chain. We have here 1, 2, we have here 1, 2, 3, 4, 5. So we should always count to the nearest end of the which has the longest substituent or a branch. So we have here the CH3. So that would be 2x2. You can see here on the second carbon of the chain, there's 2 CH3 as substituent. And we also have here on the fourth, so that would be 3 methyl. It's tri means 3 methyl, and heptane for 5 carbon chain. Here in learning activity number 4 in problem 2.12, we are going to cite along a carbon single bonded with carbon bond of propane and draw a Newman projection of the most stable conformation. Draw a Newman projection of the least stable conformation. So my example here with the carbon single bonded with carbon of a propane, which is C3 and H8 with this possibility. So you can see here on my drawing the illustration, and there's the 4 probability here illustrated for conformation with different angle. First angle here which is the carbon 2 and carbon 3, which is an eclipse conformation. So you can see there how unstable it is. You have also here the angle of carbon 1 to carbon 2, and you can see here on the illustration on its staggered conformation. We also have here the eclipse of 3 and 1. It's along with its conformation. You can see that here it's eclipse. So we have here the number 2 carbon and number 3. So you can see that there. So staggered conformation along with the angle 3, C3 and C2. So you can see that there how stable it is. And moving to problem 2.16, the proposed skeletal structure for the following molecular formula. We have here the C4H8. So C4, that would be 1, 2, 3, 4 carbon chain. There B here, we have C3H6 and an oxygen. So again, 3 carbon chain, 1, 2, 3. And C4H9 and chlorine. So C4, that would be a 4 carbon chain, 1, 2, 3, and 4. So we have also here in problem 2.18, we are going to give the IUPAC names for the following cyclocanes. So you can see here, we're just going to put the end. So we're going to begin counting the carbon chain or the parent name on the closest end to the branch. So we have here the CH3, also have here CH3, either we can start here 1 or we can start here 1. So start here 1, we have 2, 3, 4, 5, 6. So that means on the first one we have a methyl, and on the fourth carbon chain we have another methyl, so that would be dimethyl. Since there is 6, that would be hexane, and it's a cyclocanes, that would be 1 and 4 dimethyl and cyclohexane for 6 carbon chain. We have also here the this carbon, so we can, this compound, so we can see here that in this area there is the longest substituent, longer than this one, so we're going to begin counting here. That would be 1, 2, 3, 4, 5. So we're going to since this is ethyl, you can see that on the first carbon, so that would be 1 ethyl, and on the third carbon chain we have the methyl, and so because of its 5 carbon chain, we have butane, that is 1 ethyl, 3 methyl cyclopentane. And on the letter C, you can see that here the longest branch or substituent, we have the isopropyl. So we're going to begin counting here. That would be 1, 2, 3, 4. So we go into see, you can see that here that is 1 isopropyl cyclocanes. So again, this is problem 2.21. Draw both cis and trans isomers of 1 and 2 dibrosylglobutane. So since that is 1 and 2, there would be the bromine present in the first and second carbon chain. So we're going to draw that here, so that would be 1, 2, so 4, that would be butane. 1, 2, 3, 4. Also have this one, the 1, 2, okay, I wrote that wrong, 4, 3. Okay, so see the difference here. The trans is less stable, as we can see here on this plane the difference, which is on the front plane and the back plane. Well, this one is on the present on one plane, so that is a cis isomer of 1 to dibromosylglobutane, and also the trans isomers of 1 and 2 dimethyl cyclobutane.